The goal of this lab was to analyze the motion of an object that was traveling at the same speed over a certain period of time. The object of choice was an orange stress ball with a mass of approximately 0.035 kilograms. A gentle push was applied to the ball to give it an initial velocity of 0.650 meters per second in the x direction. The initial velocity was calculated using the equation velocity equals delta r over delta t, where the final position and final time was the ball's position and time after one frame, as you can see in the calculations above. The tracker program allowed me to analyze the path of the ball in the x direction by plotting the ball's center of mass in each individual frame. The program also inserted the ball's position in each frame into a data table and plotted a graph with the ball's position measured in meters on the y-axis and the time measured in seconds on the x-axis. The subsequent graph showed the ball had a relatively constant velocity, as the graph of the observed position over time had a positive constant slope. When analyzing the ball's motion, I chose to orient the axes so that the origin was at the ball's initial position, and anything to the right was on the positive x-axis. If I were to orient the axes differently by switching the positive x-axis and the negative x-axis, then all the position data would have negative signs on them, as opposed to the positive signs shown on the right. And the position versus time graph would have a negative slope, and the velocity value would be negative as opposed to positive. While these values may change, the magnitude of velocity is still constant and the net force is still zero, no matter how I position the axes. I then used GlowScript to create a computational model to compare the observed motion of the ball to the constant velocity motion predicted by the model. I used the code in Figure 1 to create a computational model which takes into account the object's mass, the net force of the object's motion, and the ball's velocity to chart its predicted position at certain intervals of time. I've circled three significant parts of this code. The ball's velocity at a certain point of time, which is equal to its velocity in the previous frame plus the net force divided by the mass multiplied times delta t, which is the velocity update formula. Although the velocity will not change over time because the right side of that line of the code is 0. Because above this line, I also added a line that says the net force vector is 0 in all three components, x, the y, and the z direction. Below those two lines, I added a code that calculated the ball's current position by adding its position in the previous frame to its current velocity times delta t, which essentially is the position update formula. After adding these lines of code, I ran the program, which created two figures which are shown in Figure 2. You can see that the predicted position versus time graph looks very similar to the observed position versus time graph. The velocity versus time graph below it is a horizontal line with a slope of 0 because the velocity is not changing over the time interval. To get a better look at the observed position versus time graph and the predicted position versus time graph, I plotted the data points for both graphs into an Excel sheet and plotted one graph containing both lines. As seen in Figure 3, the two lines are the same except for later on in the time period where the observed position line trails off, which may be because of human error in plotting the center of mass, or because the ball starts to slow down near the end of the video. All in all, the overall takeaway from this lab is that an object with constant velocity has a net force vector of 0, because the net force is equal to the total change in momentum over time. But when there is no change in velocity, there is no change in momentum, because momentum is equal to the mass times velocity. We were able to see this clearly when we plotted the ball's position versus time graph, which resulted in a velocity versus time graph with a constant 0 slope. To get a deeper analysis of the net 0 force acting on the ball, we can draw a free body diagram to see the x and y components of the forces acting on the ball. Here's the free body diagram that I've constructed, and in the x direction you can see that there's a force in the positive x direction, which is the initial force of my hand pushing on the ball. But there's also a force in the negative x direction, which is the force of friction created by the carpet, which is countering the motion of the ball. As shown in the equation above the diagram, these two forces have the same magnitude and cancel each other out, leading to a force of 0 in the x direction. The same thing happens in the y direction, where there is a normal force created by the ground in the positive y direction and a gravitational force in the negative y direction. These forces also have the same magnitude as each other, resulting in a zero force in the y direction. While these may not be the only forces acting on the ball, they are significant ones that we can point out to say that there is a net force of zero in both directions, resulting in the constant velocity of the ball.